Okay. We'll get started in just a minute or two, or very soon, if you can sit down. Okay, it's my pleasure to welcome all of you to this November edition of the TCIPG seminar on technologies for a resilient power grid. For those of you who might have been here in person on Monday and Tuesday, thanks very much. It was a fantastic TCIPG industry workshop. We gave everyone a day and a half to rest, and now we're all back together for the workshop. But as I said to Deepa, it's wonderful, and instead of us having a technical meeting, we get to listen to her talk about some technical things this month. So I'm very honored today to present Deepa Kundur. Deepa comes to us from Texas A&M. She received her bachelor's, her master's, and her PhD all in electrical and computer engineering, all from the University of Toronto in Canada. In January 2003, she came to Texas A&M, where she was an assistant Texas A&M, where she's an associate professor. Before there, she was an assistant professor at the University of Toronto, where she was the Bell Canada Junior Chairholder in Multimedia and an associate member of the Nortel Institute for the Telecommunications. Her interests include cyber physical systems, as I guess is evidenced from the title of her talk, and also cybersecurity of the electric grid. And this combination of looking at cyber physical systems in a fairly foundational point of view, but with practical application to the smart grid, I think is really interesting. So without further ado, I'll introduce Deepa. Thank you very much for coming, and we look forward to your talk.
Thank you very much, Bill. So as Bill mentioned, I'm going to talk about cyber physical systems and modeling and how this relates to the problem of smart grid cybersecurity. The work I'm going to talk about is really a collaborative effort between my research group and the research groups of two other faculty at Texas A&M University, Karen Butler-Purry, who focuses on power systems, and Takis Sorntos, who focuses on dynamical systems. So what we hope through our collaboration is be able to merge our expertise to look at the smart grid cybersecurity problem. Now, we all know, I'm sure everybody in TCIPG knows, that in our vision for a smarter grid, we're essentially looking at the smart grid as the marriage of information technology with the existing electricity network. And so the new interesting and fun stuff is that there's going to be bidirectional information transfer and bidirectional energy transfer. And there's very classical reasons to cyber protect the grid. And we all know there's technical reasons. There's increased opportunity because of the cyber enablement. There's business reasons too, because you want to be secure. Vendors of smart grid devices want to be secure to have compliance. And there's also issues of public welfare, terrorism, physical damage, cascading failures that can harm society. But what I like to think of is I like to look back at history. Okay, and if we look at the cyber enablement of a number of different services, commerce, entertainment, and even friendship, that can give us hints as to why we really need to cyber secure the grid and may give us a different perspective. Now with commerce, when we cyber enabled it and we had e-commerce, it provided a lot of advantages. One being that there was greater consumer and vendor centricity. Okay, people now were able to reach markets they couldn't before. So it, in some sense, helped the little guy, the little vendor, little artists. The entertainment industry, when it was digitized, also enabled more flexible business models. Now we can buy a single song on iTunes instead of having to buy an entire album. So we've all really experienced the cyber enablement. Friendship as well. Now, social networking has allowed us to keep in touch with geographically distant friends. So there's all these advantages, but we've also seen that the vulnerability has shifted. And we're seeing that there's been a focus also in security when we've cyber-enabled these systems. Impersonation is one issue. with e-commerce, piracy with digital entertainment, and privacy with friendship. So we would then expect there to be security issues with cyber enablement of the power grid. So the lessons learned from these systems are well known. Cybersecurity should be part of system design. Okay, so trying to apply cybersecurity later on will lead to inefficiency. Cybersecurity in these applications is really a support service that shouldn't hinder usability. Okay, so if things are difficult to use, people may not use security mechanisms. And cybersecurity is a process. So no system is completely secure, so it's always a process of identifying new vulnerabilities and securing them. Okay, but the distinction, I'll argue, and what my group looks at is the cyber-physical interface with the smart grid. So there was always a cyber-physical interface with commerce, entertainment, and the other applications, but with friendship. But that interface tended to be much simpler than we see in the smart grid. In the smart grid, the cyber-physical interface is intrinsic and deals with a lot of actuation. You have the cyber system changing the physical system. So for this reason, there are, we will argue, greater vulnerabilities. So the fundamental R&D questions that come to mind are these. What are the electrical system impacts of a cyber attack? Okay, so if we look at things in terms of information, or in an information-centric view, we want to avoid certain things. We want to provide services like confidentiality, authentication, but in terms of the smart grid, it's important to understand, what impacts they will have on the physical power delivery service. Also, how should security resources be prioritized for the greatest advantage? Because the electric power utilities have limited resources. What components should they harden first? And is the new data and control worth the security risk? So with all this information coming at us to help control and have a more efficient power system, at what point does it become too much information in terms of security risk? Now, in terms of speaking with electric power utilities, we found that attacks on information accuracy, attacks on timely delivery, and attacks on access control are of primary interest. And there's been a lot of recent research work that has focused especially on the first two, attacks on information accuracy, the false data injection attack work, and also attacks on timely delivery, which has been addressed in the research community as denial of information access. And the design mantra up until now has been that cyber assets are targets of cyber attacks, so we should protect them. Okay? And by cyber assets, these are any devices or components of the environment that support the information-related activities, so the IEDs, PLCs, RTUs, or whatnot. Now, the previous work, and I know Rakesh did some very good follow-up work that looked on false data injection attacks, looked at corruption of measurement devices. And so here you had the power system, the SCADA system, doing the job of state estimation, and there was a bad data detection algorithm that would try and detect problems in the measurements that were being sent for state estimation. And so an attack was cleverly devised whereby if the H matrix, or the configuration of the power grid, the local information was known, then you could add a bias to the measurements such that it was possible to pass bad data detection and yet have an incorrect state estimation. So this really addressed the first interesting attack, especially for electric power utilities. Now, in terms of denial of service attack, there has been a great deal of literature that's looked at what do you do if the information's delayed? You have old data. How do you control the system? How do you react? What if you don't have the information at all? And so there's been a lot of work and some very interesting control theoretic work in this area that has dealt with this problem, and they've taken more of a cyber-physical flavor because they're using models of the actual physical system to help in understanding how these attacks would affect control of the power grid. You can also see it in the computation of risk. Risk, as we know, is the probability, is equal to the likelihood of an event, an unwanted event, times the impact of that unwanted event. And the risk-based community looks at, for power systems, it details the threats, vulnerabilities, and impact areas. So in terms of the work that NERC is doing in the Smart Grid Task Force, these are fairly detailed. But what is well known is that the impact is something that's unknown, because the smart grid is an envisioned system. So how these affect the power delivery is really important. And so a lot of research has recently looked at how you would combine in a simulation environment the information IT simulators, communication simulators with power system simulators to do, for example, what-if analysis to understand the effects of cyber attacks on the power system. So we would argue that the emerging design mantra here is that cyber physical assets are targets of cyber physical attacks, and one must take into account the cyber physical flavor of the problem. And by cyber physical assets, we expand the definition of cyber asset to include those involved in energy-related activities, like generators, transformers, transmission lines, buses, and loads. So if we take a cyber physical perspective, the first thing that's interesting to look at from a research perspective are the vulnerabilities. So if we look at both the interactions between the cyber and the physical, what new vulnerabilities emerge? And this is what I'm going to talk about in part. Now, cyber assets can be direct targets of both cyber and physical attacks. Okay? You can blow up a cyber asset so that it no longer can function, or you can okay. Should I? Oh, okay, it's gone. All right. Okay. Or you can cyber attack it, and you can use a worm or virus to disable it in some way. Now, physical assets can be direct targets of physical attack or indirect targets of cyber attack. So the attacks, the false data injection attacks on state estimation, do that. They're indirectly trying to affect the physical system. So in terms of cyber physical attacks, the interesting emerging field has some evolving definitions. From the simulation and modeling community, people are very interested in looking at cyber and physical attacks that are coordinated. And they are applied to the cyber physical assets with the goal of maximizing physical disruption. So for example, it could be a combination of transmission line fault with state estimation modification to achieve a certain instability in the system. There's also another evolving definition which relates to the work I'm going to talk about, in which a cyber attack can be employed on a cyber asset, but the goal is not just from an information-centric point of view. The goal is to disrupt the a physical asset in particular. And what I'm going to focus on is control signal modification to reconfigure a power system, for example, to an emergency state. Okay? And within this cyber physical attack perspective, we see there's a grand challenge emerging, and that of modeling the cyber and physical interactions. So within the cyber physical community, there is a wish list, okay, and how we model these things. We talk about needing tight coupling of cyber and physical components. So there has to be an integration. The cyber environment is discrete time, the physical environment is continuous time. So there should be a convenient way to integrate this into an effective model. And in particular, we're looking at effective models to help with vulnerability identification. Also, in terms of modeling, simulation is excellent, but are there also mathematical models, analytic models with a formalism that can be borrowed, that helps and provides power in terms of the vulnerability analysis? Also, are you able to vary the granularity of modeling detail to be able to tune the complexity? And is what-if analysis possible? So this is really the wish list that's emerging, and there's other factors, but for our work, this is our wish list for modeling, for vulnerability analysis. Now, within the work that my specific group is doing, we are looking at using dynamical systems for this task. Now, in a very general sense, dynamical systems describe the time evolution of a state vector. Okay? And so in terms of modeling the power grid, this could be voltages and currents. It could also be the frequency and phase of a particular synchronous generator, for example. And the dynamical systems have been used in the past to effectively model components of power systems. So this tool set has a lot of power to it. It can be used, and in some contexts has formalism. It allows for variable granularity. Okay, depending on the order of the model, how nonlinear it is, you can vary the granularity. And it may be possible to do what-if analysis. So it has those advantages. But one question we have is, how can we model using a dynamical systems framework, both the cyber and physical entities? And so if we can borrow these tools from the dynamical systems community, we may be able to create a very good vulnerability analysis tool. So the work that we're doing overall in the group is we're looking at effective ways to model through dynamical systems. The dynamical system modeling can also make use of graphs. So for example, here if we see we have a for example, a smart grid system. We may be able to model, essentially break up the system into components where each component can be modeled as a dynamical system. And then they can be linked. Either the cyber components can be linked. In this formulation, for example, you can have a cyber network and a physical network, and there's a cyber-physical bridge that may be used to connect the system. And each node in these graphs could have a dynamical system equation to represent its behavior. And this is one modeling framework that we're looking at. And so you can take, for example, very simple 13-node IEEE system and represented as a graph, and each node here, the colored nodes would be the cyber components, the white would be the physical components, and you could model an attack and understand from this graph construct, how it would propagate within this system. So there's that perspective. I'm going to talk about a little bit of a different perspective. So we said that the power community is interested in attacks on information accuracy. So this is the false data injection attack community is doing some very interesting work in this area. Attacks on timely delivery. So that's the denial of access, denial of information access. And what we're focusing on in this work is attacks on access control. So in particular, we're going to focus on what we call reconfiguration attacks. So we're studying a new form of vulnerability. Now, in terms of the evolving definitions of cyber-physical attacks, we're looking at this one here, in which a cyber attack directly tries to achieve a certain instability in the power grid. So this work is entitled Coordinated Switching Attacks. And here, the smart grid, it borrows really from the cyber enablement, the connectivity that's envisioned in the smart grid. So if there is remote access to circuit breaker switches or relays, this allows somebody to control the actuation within the grid. So, for example, if breaker control signals through such attacks can be corrupted, we're looking at ways to exploit physical vulnerabilities from this reconfiguration to achieve a physical disruption. So the goal here in this class of attacks is to achieve physical disruption through rotor angle instability. Okay? So we're going to model the generators in the system and as dynamical systems and see if we can create an instability. And so we exploit local state information to define a disruptive cyber control switching sequence and model the cyber physical system as a type of hybrid dynamical system. Okay, so our modeling makes use of hybrid dynamical system. And we think this is an interesting way to model a system because it very conveniently achieves both continuous and discrete behaviors in the model. Now, within hybrid dynamical systems, there's different classes. And the ones we're looking at are variable structure systems or switch systems. And in a very general sense, a switch system does this. There's a number of subsystems. For example, we have F1, F2, F3 to Fk. And there's dynamics associated with each of these systems. And in a variable structure system, there is a switching signal we define here as S of X. In this formulation, it's a state-dependent switching. It doesn't have to be. It could be, also time-dependent. And the dynamics of the overall system change according to the value of the switch signal. So the switch signal may be such that it identifies that the switch position should go to one of the subsystems. So this is the type of model that we're looking at, and there's a very nice body of literature analyzing these systems. So if we consider, just to elucidate the problem more, switching between two systems, this is what we essentially have. Okay? So X dot, the dynamical system equation, can switch between dynamics F1 and F2, depending on the sign of the switching signal. Okay? So if the switching signal S is positive, then it will have dynamics F1. If it's not, if it's 0 or negative, we would have dynamics for F2. Okay? And so this can be used to model a lot of different systems. For example, in a very straightforward way, you can see that this can be used to model a load shedding scenario where the switch could either serve load Z1 or Z2. Now, if we look at a very simple linear model here, so X dot can be equal to dynamics A1X, where A1 is a matrix, or A2X, where A2 is another matrix. For example, say these are matrices. We've just sort of used this as an example case. Then you can see the dynamics of the system can be represented with these phase portraits. So here, if we go back here, the X state is a vector, and it has two elements, x1 and x2. Okay, and it can represent a particular voltage and current in this system. Now, if we look at the trajectory of that state x, and so the horizontal axis represents the value of x1, and the vertical axis the value of x2, we can see the trajectory. And I'm not sure if you can see this, but there's tiny arrows showing how the trajectories converge to the origin in both these cases. Okay? Now, this trajectory is if the system had the first dynamics, and we call it the A1 mode. And this other second diagram is if we had the second set of dynamics, or we call it the A2 mode. Okay? So we get these behaviors here. So both these systems are stable, and essentially if the switch is in a static position, the system will be stable. Okay? Now, what we leverage in this class of attacks is this idea that you can switch, and there exists a switching sequence that even though if in a static position the subsystems are stable, you can create instability in the system. Okay? So going back to our previous example, if we the problem is that of designing a switching sequence or a signal S of X. Now, we can look at two possibilities, for example, okay? And we constrain ourselves where S is a linear function of X. So these are very simple switching functions. So the first is x1 plus x2, and the next one is negative x1 plus x2. So in both these situations, if we switch according to that logic, we see an emergent behavior. So if both of these plots show the A1 mode and the A2 mode, the A2 mode is shown in green and the A1 mode is shown in blue. And so as you can see, both of them, if there's no switching, will converge to the origin. Now, if we use this switching rule, x1 plus x2, you can see that when you switch between the systems, initially, that line essentially is here, by the way. It's this line with slope -1 that passes through the origin. So once the state trajectory passes over that, there's a sign change in S, and so you switch to the other system. So anytime there is a change, you switch to the opposite. So if you started here on the blue, you would switch to the red, and then you can see after a while there's an emergent property that occurs. Okay, in fact, this red line here demonstrates how the state starts to leave the area of the origin and go to infinity. Okay? In another case, if we use negative x1 plus x2, you can see again we've got the A2 mode in green, the A1 mode in blue. You can see that the switching sequence allows the state to converge to the origin. So in both these cases, what we have is an emergent property that neither subsystem has, but that can be used to steer the state in a different direction. Okay? In one case, you can create instability. In the other case, you can still disrupt the system, but you can steer it to the origin. Okay? So this is called the sliding mode. And the sliding mode is an emergent, it's arguable. People in this community will argue if it's emergent because we can design it. So typically an emergent property is an uncontrollable property, but it is a surprising property from the switching that has characteristics different from the individual subsystems. Okay? So even if somebody has designed a power system or designed a system that behaves perfectly in a static switch situation, this emergent property may exist. And the motion of the state trajectory occurs along a chosen line, plane, or surface. And this is called the sliding surface. So whether or not we can harness this to identify vulnerabilities really depends on its existence. Now, the existence of a sliding mode in general is this. These are sufficient and necessary conditions for the existence of a sliding mode. These could be locally required as well. It does not have to be a global result. So you have the switching surface S. So what we need are these two limits to be these two limits to occur, these constraints, which is effectively equal to this. So S times S dot should be less than 0. Okay? And so S and S dot can be found by the dynamics here. S dot is defined also, is related to the dynamics F1 and F2. So we need that. Now we can look at this visually as well. So for example, say we have this sliding surface here. The sliding surface is the surface given by S is equal to 0. Okay? So S is a function of the state X, and S of X is equal to 0 gives you a surface. So in a 2D situation, it would be a curve, or we're looking at linear models, it would be a line. Okay? Now, when S is greater than 0, it would be on one side of the line, okay? And when S is less than 0, it would be on the other side. So what we would like is the sign of S dot to be the reverse. So that would define the trajectory of the system towards the sliding surface. So if you're on the S is greater than 0 side, you would like the trajectory to be driven to S is equal to 0, which is what this sign will, this limit here will do, this condition. And when S is negative, you would like it to be driven to the sliding surface as well, which is what this limit would provide. So this provides that convergence to the sliding surface. So if you can do that, you can re-steer the state. You can either bring it back to the origin for a stable situation, or you can let it go to infinity. So this is the property that we're making use of. So if you were to use this and create an attack, how would you do that? Okay. So attack construction, I mean, we can create an algorithm to see how we could use this, but attack construction basically can be broken down into 3 steps. So you can represent the smart grid system as a variable structure system whereby, you know, S of X is generally left, but you have analytic models for the overall system, dynamical models. After this, you can determine the existence and identify any sliding modes that exist, and then assign a sliding surface for attack. So these are the 3 basic steps. The reason details aren't given is really depends, how you determine the existence of the sliding mode really depends on the models that you have in the first step. So this is what our attack construction does. So we've looked at it in a number of different IEEE test systems, and I'll show you the results for the Western Electricity Coordinating Council 3-machine 9-bus system, and we've modified it a little bit to, you know, and I've shown you in red what that modification is to make it more interesting, and we've added a switch here basically. Okay, so in this scenario here, we've added another generator, G1, and there is a load connected here, load PL. Okay. So we'll look at how you can create a switching attack for this system here. Okay. So in step 1, there's many ways to model it. If we, for example, model G1 as being connected to an infinite bus system, and we use the swing equations, and we have the switching of the load PL. For a given set of parameters, we have a paper on this, so we can show you in steps what the model is like. This is the variable structure system that can represent our previous model here. So this is the modeling problem. So if PL is connected, we have this situation here. If it is not connected, we have these dynamics here. Now the state that was defined as X previously has two components, delta 1 and omega 1, that represent the phase and frequency, the normalized frequency of generator G1 here. Okay, so these are the states of the system. So now if we can create instability in terms of these states, we can create rotor angle instability in the power grid. Okay, so the existence of the sliding mode. We've derived theorems that look at, the existence conditions for the sliding mode under a number of situations, for example, when the models are linear or low order, whatnot. But in a very general sense, the existence of the sliding mode can be considered graphically if you've got the phase portraits. So we here have the phase portraits of the system A1 and the phase portrait of system A2. So here A1 and A2 are these systems here, okay? The A1 is when the load is connected, A2 is when it's not connected. Okay? And one means to identify the phase portrait is to overlap both of these and see if they tend to converge towards a line, okay? And that line will then represent a sliding surface. Okay? So this is really a graphical interpretation, but there's analytic ways to do it if, for example, you have linear models. There's a body of literature to provide analytic means. But to give you an intuitive idea of how this sliding mode exists, we can look at this graphically. So we have our green trajectory here, which is the phase portrait of system A1, and we've got the blue, which is the phase portrait of system A2. Okay? And the red represents a stability boundary of the system A2. Now, in terms of dynamical systems, you can identify equilibrium points of dynamical systems. So these are points that they're attracted to. You can also identify saddle points. And if you identify a saddle point, you can use the Jacobian information about these points to identify if there's equilibrium or saddle points. And if you run the system starting at the saddle point in forward or reverse direction, you can identify the stability boundary. So what this means is on one side of the boundary, if you let the system go, it will be unstable. So this relates to system A2. If you let it go over the stability boundary, and it's in a static switch position, it will go unstable. So this is what we're going to try and do. But we first want to identify a sliding surface in order to do this. So say we consider this here. S is equal to 6 delta 1 plus omega 1. Okay? And so, for example, this is what it looks like here. And so the blue is A2 and the green is system A1. And we will argue if you switch in this way, you will see you will converge to that pink line drawn there. Okay, so the green converges here to the pink. The blue also comes back and converges to the pink on either side. Okay. Okay. So this is how our attack is defined in terms of the switching law. So S will be equal to 6 plus delta 1 plus omega 1, and the sign of S will determine which subsystem you've switched to. So now if we apply switching from 0 to 2.5 seconds, so we're trying to minimize the effect for the attacker, this is what occurs. So you have here in this plot, you've got the phase portraits of system A1 and A2, and the stability boundary of system A2 is shown here in black. The trajectory of the state is shown in pink. So if the system will typically start at equilibrium, okay, the equilibrium point of one of the systems here, which is A2. Okay, and so when the switching law occurs, it is driven to that sliding surface here. Okay, in that process, it moves over the stability boundary of A2, and when the switching stops, it goes to infinity. Okay, so you have the ability to destabilize the power system in a nice formulation in order to understand what the switching law would be. Now, that's with our swing equation model of the overall system. So we have a low-order nonlinear model. But how does this really stack up when we look at higher-order models? So if we look at PSCAD simulations and use high-order models to simulate all the components, and these are, for example, the parameters that we used, we can see very similar behavior that's occurring. Okay? There is a hysteresis that we model in the switching so that it's realistic. So that's why it's not right at the line. That's why you see the switching back and forth. But this graph here it's the phase portrait. And you see how you start at the equilibrium point of one system. It's driven to the sliding surface. It goes over the stability boundary. And when the switching stops, it goes to infinity. This top right corner represents the deviation of that generator from the nominal frequency. And you can see that it just, you get the rotor angle instability. And this is the associated phase angle of G1 and then the output voltage. Okay, so overall, we're able to destabilize the system. And depending on the protection that exists, it can have effects on the other components as well. So final remarks. So we've introduced a class of coordinated variable structure switching attacks that represent a new class of attacks aimed specifically to disrupt power system operation. So the difference here is our cyber attack has a specific goal in mind to disrupt the physical system. The models that we're using are hybrid dynamical system-based models. And we're looking at this tool set beyond the switch system tool set to effectively model cyber-physical systems for vulnerability analysis. So in terms of the community at large, the cybersecurity smart grid community, where should we go from here? Okay. One of the things in talking to a lot of people that is important is to develop common problem formulations in the community. In that way, our solutions, our models can all be compared and related within the same context. We should also, and I think this is something that TCIPG knows well and is doing very well, encourage greater collaboration amongst the power system researchers, control theorists, and information technology community. And if you want any more information, you can ask me questions now, or you can contact me offline.
Okay. We have time for questions, and there are questions coming in online. So we'll ask those as well. So please go up if you'd like to ask questions.
This question is from online. I hope I get it right. The approach assumes that you have a complete knowledge of the system and machine dynamics, I think the word was used. But in an attack, you may not have all that information, so how does that affect
okay, so
your approach?
This is a good question. The work we're doing now is trying to, I didn't present it here, I was trying to give an overview, is trying to identify the robustness of the approach. You need to know the state, and you need to know a general configuration of the power system locally. In our experiments thus far, the overall approach, the attack construction seems robust under many different deviations in the model. For example, if we take the power system and we assume lack of knowledge of some components and assume that we only are comfortable with linear models, and we create an attack from that model, and then we put it into our PSCAD simulations, we find that the range, so we put it into our PSCAD simulations, and typically when you identify an attack, you get a range of parameters for the switching law that work. And we find a very large overlap between the parameters that we find work in the highly linearized system and the ones in the PSCAD simulations. So to us right now, it appears to be fairly robust. Yes?
Nice presentation. I enjoyed it. You probably don't know this, but maybe you've talked to Karen about it. To do this, you're switching with a circuit breaker. I'm not a circuit breaker expert. I know that we use them to open and then we can reclose them. But do you know how many times you can cycle a breaker? Yeah. So this has definitely been something we've been talking to Karen about. We've been modeling
that there is an effective hysteresis on the switch. And it depends on the type of breaker, and it's, it could be on the order of milliseconds. Now, the switching I showed, that occurred in about 2.5 seconds. And I believe there was maybe 5 switches that occurred. 5 switches within 2.5 seconds. So the way we've tried to address it is to create a hysteresis that works in our simulations.
So how are you doing the analysis? On the linearized model of the system or on the nonlinear system?
The goal of the analysis is to identify a switching rule for an attack.
Yeah.
We have done both. Okay, we've looked at both. We have looked at we have derived existence conditions for this vulnerability for linear models of the system. So we've taken a linearized model of what you see, and then we've developed attacks for that. We've used the low-order nonlinear swing equations that you saw and developed an attack for that. And then we've tested both of them on the PSCAD simulations and used high-order nonlinear models for the components. So there appears in all of those cases to be an overlap. So what model do you use? This is, at this stage, it's an ad hoc thing. If you're going to use nonlinear models, it becomes difficult to identify the existence of a sliding mode because you have to do it visually. If you use linear models, you can definitely use theorems. And so we are tending to go towards using linear models because then you can use the theorems to identify it and apply the attack, and there's a great deal of overlap in terms of the space in which the attack works in the simulations.
But if you use a linear model, basically as you are doing the switching, the system trajectory is evolving, so the matrices of the linearized model are going to be time varying. Are you guys considering that in the approach?
Can you repeat that one more time?
So as you are doing the switching, the system obviously is evolving through along a trajectory. So what you guys are doing with the linearized model is just basically linearizing along that trajectory. So the matrices that realize are time varying.
Okay, I'm not sure if, so we are modeling for the purpose of identifying the attack,
right?
Not necessarily to exactly model the behavior of the system. I mean, that is definitely necessary to reasonably model it to identify the attack, but the goal is to identify the attack. Right? So in terms of our linear models, we don't deal with the time-varying nature that you're discussing.
Okay.
I would think we're looking at such small time scales. I'm not sure if that matters or not. But
okay.
in terms of the systems we're looking at, we're looking at basic test systems used in the power community. It does not seem to be an issue so far.
Right. I mean, for the single machine infinite bus that you had there with the classical model,
yes,
the linearized model you get is just basically time invariant. But yeah, so if you go to higher order models, then you're going to have like a evolution of the system. So that's one thing. The other question that I had is the loads. You know that the canonical model we use in power system is a differential algebraic equation model. So how are you guys handling the algebraic part? Are you assuming just impedance loads, or how are you handling the algebraic part of that model?
The loads, I believe, so we're looking at different classes of loads. In these simulations that I showed you, I believe they modeled it as constant impedance loads.
Okay,
yes,
so that's why it renders like a OD instead of the DA. Okay, that's all. Thanks.
Hi, this is Bill Sanders. I'm just encouraging people to give their names when they ask questions. My question's a little more on the cyber side, and I think it is nice that you're exploring the physical side so well. Have you thought about what cyber type things need to happen in order to implement this attack? And would those models ultimately need to be integrated in as well? Or do you think there's sort of a pretty clean separation that you know exactly what you need to do so you can model the two sides separately and then combine the results?
Yeah, that's a good question. In the formulation I show here, we've assumed a clean separation. Now, because, we're looking at being able to corrupt, switch control signals, you can borrow, for example, historical risk analysis values to understand the likelihood of being able to do that. Maybe, okay, you can do that. There are other formulations where that clean separation does not exist. I would say, and I didn't talk about it here, but in terms of looking at, if you look at an attack on information, then that then will be used to control the power grid. You have more of that interaction, and we're trying. And then in that sense, the goal of would be to maintain stability in. With delay information, with non-existent information or corrupt information. So in terms of those formulations, I found it naturally leads to a very nice cyber and physical integration. But in terms of what we're looking at here, which was really trying to see if a single switch could react, could create havoc within and cause disruption, we were assuming something clean. Because we think it's just one switch that really needs to be corrupted, and it didn't seem like too much of an issue. If we look at multiple switched models, where you can have multiple switches switching, then for sure you'd have to consider the likelihood of corrupting the different switches. And so you would see more of that interaction.
This is Tom Overby again. Bill encouraged me to say my ID too. We're doing studies using a real power grid model, and we do switching in a corrective sense, that during a disturbance you have to switch, and some utilities have very specified processes for doing this, and if you mess up on it, the system doesn't respond well. I mean, so if you're talking about an adversary, they could certainly, with very few switching actions, cause havoc on a system. So I think you're going along a very good route here. I don't want to get into too much details as to what switches will do this, but there are switches that'll do bad things.
Yeah, what we were looking at was to do it very quickly. So so it was a targeted thing, but that's very good to know.
Hi, this is Rakesh. Nice presentation. One quick question, Deepa. So you did an example with a single switch, and I was just wondering about the complexity of the models. If there are multiple switches, would you then can still represent it in dynamical system with just one switch, where you would model the equivalent systems when in different switch positions? Or rather, you'd have to deal with some other complex model?
Okay, so the question is, if you had a single switch... If
you had multiple switches.
Oh, no, you could still do it as a dynamical systems formulation, for sure.
But then would the model get more complex?
Your number of subs... Okay, so what will happen is your switching surface will increase in dimensionality. So the reason I showed the results, I mean, we're looking at cases like this, but the reason I used a single switch is you can visually see what happens to the state, right? But no, your switching surface no longer becomes a line. It goes into n dimensions in general.
Yeah, so. And in that case, I think, like you said, linear models would be better, because then you can analytically solve rather than the non-linear.
Exactly. Stuff. Yes.
Thanks.
Prosper Panompabi. I look at the model you used with one machine connecting to infinite bus, and to the infinite bus we have a switching load. We have two loads which define the state 1 and the other one for the state 2. So try to connect this with the real application. The state 1 might be connecting to the load 1, and the state 2 is connecting to the load 2. So my question was to know, can I get some real definition of the state x1 plus x2 and the state minus x1 plus x2? What it might be exactly in the power grid.
Okay, that was actually an artificial, a very clean artificial example given. The later one, where you look at how when we consider the WECC system, that one, the states are the state here. Okay, this is a good question. Let's go back here. Let me go. Okay. Let's maybe look over, oh here, maybe this one here. Okay. Does this do it? Okay, it's F5. Okay. Oh no. Okay. Sorry, I'm a Mac user. I'm terribly sorry. Shift F5? Okay. 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 Let's do this one here. And it's Shift F5. Okay. Okay. So here, okay, the interpretation of the state was, this was the normalized frequency of generator G1, and this was the phase. Okay. So this was the sliding surface that we essentially found. Okay. And the equation is 6 delta 1 plus omega 1. Okay. And so the question then is, what physical interpretation can you give? Okay, okay, in terms of, instead of looking at the switch, okay, this is what this is. So this is not the only switching surface. There's a whole family of them that will destabilize it. This is one I've shown as an example. So you can, I think plus or minus definitely, plus or minus epsilon, for quite a large epsilon, you can do the 6 and as well to unity, and you will still have a valid switching surface. What is happening is basically this. So when in all of these systems, the way you can achieve instability is in part because you're making use of the non-minimum phase properties of the subsystems. So you could, and we're looking at situations where in static switch positions, things are stable, and you would expect that. But when you switch, there's an initial transient, and if it's non-minimum phase, it will go up, okay, and then come down. Now, if you keep switching, okay, and then there's an initial transient, and you switch to another system before it has an opportunity to come back down, then you keep building on it, and you create instability. I believe that's the property we're making use of.
Okay, thanks.
Okay?
Hi, very nice presentation. I'm not a power expert, as you know, right? And so I have a cyber question. So if I am an attacker, right, and you are going to help me how to attack the system, how would you help me to make this system unstable using your analysis? Would you tell me which switches I need to, open or close, and which of them I should do in the same time or different time, or what would be the kind of, let's say, advice to the hacker which you could give?
Okay, so what we're looking at now is we're using this to develop a vulnerability analysis tool. So we look at a given grid configuration, we assess for every switch how easily you can apply this attack and how robustly you can apply it to destabilize the system. So what this can provide an attacker is information on where there exists a weak point if you wanted to apply this type of reconfiguration attack. It can also give the attacker a family of parameters that you can use for switching to be able to achieve instability within a short period of time. So that, it equips the attacker with a family of rules that they can use, and prioritization of the switching to be able to achieve it quickly and robustly.
So are there any more questions either online? You can type them in the comment box. We'll give you a minute to do that, or locally here. It's great. Oh, Roy has a question.
Yeah. I mean, wait. So what is the analysis, the dynamical analysis that you've done on those circuits? Are there second order and third order analysis that can be made?
So we used the swing equations, so they're second order nonlinear.
Right.
Okay, so
okay, so can you do a higher order?
No. So you could. It would. You definitely could. We used a very convenient formulation. The PSCAD simulations are on high order nonlinear. models. We used low order models because it seemed much easier to identify the sliding mode. But when applied to the high order model in simulations, the numerical models, we achieved instability for almost exactly the same range we identified with the low order nonlinear systems models.
And do those, what's the nature of those sliding windows when you've got a higher order?
Okay, so I'll give you, first of all, no, this is not it. So what is the nature of the, so these are the models. Shift F5. Okay, so these are based on the swing equation, these models here. And so your question was, what was the effect?
No, what would it look like? I mean,
if
conceptually, if you had a higher order, would it be a straight line, or would it be some?
Okay. So to identify the sliding mode, it's just a matter of when you look at it visually, it doesn't have to be a straight line. Okay. You could look, for example, if we go here, you could look for any curve that would go, like it doesn't have to be a straight line. Analytically, to be able to get parameters to equip an attacker, we assume a straight line. That's something that's specified by the designer of the attack.
Okay.
But it does not have to be a straight line.
Okay, thank you.
Okay, I think we're almost out of time. Oh, there seems to be an online question coming in as we, just a second.
The question's is how does this approach scale to a large size network?
Okay, the dimensionality for modeling and the sliding surface naturally scales up. The dimensionality of your state vector scales up. This is where it becomes very useful to make use of linearized models, because you can still identify more easily the existence of this attack under linear models. So it scales in terms of, for example, if you want, it depends on the modeling approach you use. If you add 2 states for every generator you add, okay, your dimensionality of your state vector goes up, 2 for every generator you add. If you increase the number of switches that can be switched, the dimensionality of your sliding surface goes up.
And one last question, will there be a way to detect this kind of physical attack?
I think if you're monitoring the system, it's very clear that you will see instability in the state of the actual generator. You can. So if somebody is carefully monitoring, you should be able to see it. And in terms of mitigation, what we're looking at is how would you reconfigure the system so that with that particular switching pattern that's being employed, it no longer becomes a sliding mode of the reconfigured system.
Okay, thank you very much. That was an excellent presentation, Deepa. We appreciate you left some time for questions, too. Before we sign off, let me tell everyone you'll receive a notice, but on Friday, December 2, at 1 p.m. Central Time, we'll have our next presentation, and this will be by Misha Stoyer from Florida State University and part of the Freedom Systems Center, who will talk about power system-driven hardware for in-the-loop simulations at Florida State Center for Advanced Power Systems. Look forward to seeing you all next month.